Chapter 11, we are going to move into probabilities. This is more of kind of a surface introduction of probabilities, and that's honestly kind of the flavor of the rest of the semester. So we're going to briefly touch on probabilities, and then we'll briefly touch on set theory, and then we'll briefly touch on logic. And all of those sections in themselves can be and are entire semester courses in a lot of math programs. So we'll get a good idea of what they look like. But if you are kind of interested, there's a lot of material that you can get into beyond what we're going to cover. So we're going to start with some definitions when we're dealing with probability. And so first definition is an experiment. An experiment is anything where the outcome is uncertain. So for instance, you guys can't see me right now, but I'm wearing a hat. And so that's not really an outcome that is uncertain. I am wearing a hat. What is uncertain is whether or not I will be wearing a hat tomorrow. And so kind of the classic things we see with experiments are if I flip a coin, what's going to happen? If I roll a die, what's going to happen? If I pick a card, what's going to happen? Because, well, there's a multi-billion-dollar industry focused in, well, not focused entirely, but that makes a lot of its money in Las Vegas based around the fact that people are pretty bad at understanding probability and are willing to spend a lot of money in the hopes that they will win. So that's what an experiment is. And then a sample, not spade, sample space is all of the possible outcomes for an experiment. So if we're flipping a coin, the sample space is heads or tails. If we are rolling a normal die, six-sided die, the sample space is 1, 2, 3, 4, 5, 6. So it's every single possible outcome that could happen if we do a certain experiment. And so kind of the standard or the very basic intro formula that when we are trying to figure out the theoretical probability is we take the number of outcomes or the number of items in our sample space, we put it over the, oh no, sorry, take the total number of things in our sample space, put that on the bottom of our probability, and on the top, we talk about the outcomes that we are interested in. So just to kind of hammer home this flipping the coin idea, because it is a very classic example, if I want to figure out the chances of me flipping a head, what I do is that the number of possible outcomes of that is 1. It's either heads or tails, so I'm looking at heads, that's 1, where the number of items in my sample space are heads or tails, so that is 2. So I have a 50% of chance of flipping heads. Now it is worth mentioning that it is theoretical. So I'm not guaranteed that if I flip my coin 4 times that I will have 2 heads and 2 tails. It's more of a this is what should happen and this is what will happen if we start to talk about flipping our coin like a billion times. Then it is essentially 1/2 of the time will be heads and 1/2 of the time will be tails. Okay, so all that was kind of fairly technical with the definitions. It'll probably make more sense when we get into an example. So I have a dice being rolled, a die being rolled, singular, and I want to find the probability of rolling a 3, an even number, a number less than 5, a number less than 10, and a number greater than 6. And so a good way to start any probability problem is to think about what's the sample space. What are all of my possible values? So if I have a die, I could get a 1, a 2, a 3, a 4, a 5, or a 6, meaning that I have a total of 6 possibilities when I roll this die. And so then each instance here, I'm trying to figure out how many possible pieces of my sample space meet the required thing that I want. So if I want a 3, well, there's only one number between 1 and 6 that's 3. It's 3, almost kind of silly to say out loud. And so the chances of rolling a 3 are 1 out of 6. Their number of even numbers between 1 and 6 are 2, 4, 6. So there's a total of 3 of them, and our sample space is still out of 6 possibilities. And then we just always reduce if we have a fraction. And a number less than 5, so it's not less than or equal to 5. So if it's less than or equal to 5, there's 5 numbers that meet that criteria. It's just strictly less than 5. So that's 1, 2, 3, 4. I have 4 numbers that meet that criteria, and I have a total still of 6 possibilities. In fact, everything in this example is going to have a total of 6 possibilities. So I have over 6, I reduce to 2/3. Now, a number less than 10 is everything that meets that requirement. All numbers from 1 to 6 are less than 10. And so I have 6 possibilities out of 6, or I have 6 options out of 6 possibilities. And so that's 1. So that's something to mention when we're talking about probability, is that if we are definitely certain to get it, and for all intents and purposes, then our probability of getting that is 1. So if I'm flipping a coin, the probability of me getting heads or tails is 1. I can't have anything greater than 1, because if we're going to think about percentage wise, what we're finding here are decimal answers. And so if we were to convert that to a percentage, that means there's a 100% chance that that will happen. So you can't really have 200% chance of something happening. That doesn't really make sense. And so that's why the biggest value that we can have when we're dealing with probabilities is 1, or when dealing with this like theoretical probability, I guess, to be more specific. And then on the other side of things, I could ask, what is the chance of me rolling a number greater than 6? Well, there's no numbers on a 6-sided die that are greater than 6. So that's 0 out of 6 and 0. And that's the lowest probability of getting something. You can't really, at least strictly, again, for a theoretical probability, you can't have a negative probability, because that wouldn't make sense. How could you undo something happening? So that's kind of the two extremes you'll see. You'll have 1 and you'll have 0. Now, something that's worth mentioning is that, especially when we're dealing with theoretical probabilities, it's usually doable to leave things as fractions. And so that's why we tend to do so, if that's possible, because when we start to get into probability, normally in this class we round to 2 decimals, and we're going to continue that in this case. But when you get to a large amount of money or a large amount of cases or something like that, and you have a decimal, when you're starting to round that 2 decimal places, you start, those small changes start to get pretty drastic. So if we can leave it as a fraction, we do leave it as a fraction. Typically, we'll talk about experimental probability later, where that's more okay to have decimals. But in general, try to stay with fractions. Well, speaking of that, so computing experimental probability, as far as the formula goes, it looks exactly the same as what we were doing previously, except for now we actually have, we observe something. And so this kind of shows up a lot with surveys. If you're sitting on a campus and you have those people kind of standing on the corners shouting at you to talk about things briefly, they might be asking you a survey, and they're hoping to gather as many things as possible in order to get a really good probability, because that is a theme in probability, especially empirical probability. The total number of things you have, the better the chances that your probability are going to be reasonable. And so every person they ask is the total number of observed occurrences. And then let's say they asked, something simple, a simple question: are you above 6 foot or below 6 foot, or below or equal to 6 foot? And so that would be the observed number of times E occurs. So if they ask 40 people on campus and 10 people are greater than 6 feet tall, then the number of people, or the total number of times E occurs would be 10. The total number of observed occurrences is 40. Okay. Again, it's kind of easy to get lost in the definitions, although it is important to kind of technically know them. Really, in practice, this is what it's going to look like. We're going to have a table, and this, again, is kind of, I believe, maybe came from the census, ideally, of asking people 15 or older, and they asked in the millions, so there's a good sign that this is a pretty good experiment of, are you male, are you female, are you married, never married, divorced, widowed, and then kind of totaling all of those things. And that is kind of a recommended way to do surveys, is maybe not exactly this table, but this table shows up a lot because it's nice to represent, okay, I have married male, married female, so I can total that column and I get 133 people. And never married, I have 43 male and 38 female, so I have a total of 81. And then similarly, horizontally, I'd have females that 67 are married, 38 are never married, 15 are divorced, 11 are widowed. And so that means there is a total of 131 females. And then if we do have this format, that bottom right number is always going to be the number of people surveyed, or I guess the number of people surveyed that fit into these categories. So now the questions become, what is the probability that the person chosen at random is? And this is the empirical probability, because we don't have theoretical coin flips or decks of cards that are always going to be perfect. This is much more applied of, we're actually just looking strictly at the numbers. And so if we're trying to find a divorced female, while I look at my table, female, divorced, those match up on 15. So I get 15 out of my total of 254. And that 254 is pulled from the bottom right. And now, since we're dealing with empirical population, we tend to now leave things as decimals. And so again, kind of the standard is 2 decimal places. I think I'm going to do 3 decimal places on this lecture and the next lecture. But if you want to stick to the classic 2 decimals, that's fine. But write both of them. I don't want you to just write the decimal, because then I don't really see where your numbers come from. And then I have to guess, and then I'm going to guess poorly because I'll probably be frustrated at that point in my grading process. Now, very similarly, if I want to find the number or the empirical probability that someone is widowed, now I'm going to look at the total. So it's not really telling me, am I just looking at female or a divorced or a widowed female or a widowed male? It's just a total widowed amount. And so that's going to be the bottom of that widowed column. And so that's 14 over, again, the total is 254. That almost is going to show up in every calculation of empirical, because you're looking at the total amount on the bottom. And so if I do that, I do 14 over 254, which is 0.055. And kind of to reiterate, that's why 3 is a little bit more reasonable when dealing with empirical populations, because A and B would be the same answer if we rounded to 2 decimal places, which just isn't true. They are different values. But that being said, if you do round to 2 decimal places and you write the fraction ahead of it, then I'll be able to kind of track it down and say, okay, you rounded 2 decimal places, but I see how you got it, full points. And then very similarly, if I want to find the probability that a person chosen at random is male, or at least respond male in the survey, then I would total the horizontal column, get 123 over a total amount of all the people surveyed, 254, and then I get 0.484. Now, another thing worth mentioning is, yes, this is in the millions, and if you want to do it, you could write 15 million over 254 million on the left side, but it's going to be the same. And so if it gives you something like that and the table is in millions or thousands or billions, I don't want to say ignore that entirely, but when you're doing probabilities, empirical probabilities, you can kind of just take the actual numbers, because it doesn't really matter what scale you're working with. And once you divide the two, you're going to get the same result, whether or not you put a ton of zeros behind it, or if you just leave the numbers alone, because all those zeros would do eventually is would just get simplified